I'm continuing on in section 6.3 on quantum theory, and I've started here where I left off the last time. We have an energy level diagram for our most modern model of the atom, the quantum mechanical atom, and we've seen that at each energy level there are a variety of different orbitals available. Now, I left out part of the story. Before we came up with the names of the orbitals, 2s, 3d, the calculus gave some numerical addresses for each orbital. I want to be able to come up with a unique address for every single one of the orbitals. And I'm glad to have this energy level diagram to make an analogy. I think of these energy level diagrams with the orbitals in them like an apartment building. Suppose I wanted to mail a letter to a specific apartment. How detailed would my address have to be? Well, first, I would have to say which floor of the apartment building it's on, or in terms of the atom, which energy level. First energy level, second energy level, third energy level, and so on. So first I would narrow it down to a particular floor. But then I'm going to use a number to indicate which wing of the apartment building I'm having. Or in terms of these orbitals, which sublevel. Is it going to be in the S? Is it going to be in the P? Or is it going to be in the D? So I'm going to need a second label to narrow it down to a particular wing. And finally, some of the wings have more than one apartment in them. I'm going to need to provide an additional label to make sure I get a particular one of the apartments in that wing, a particular one of the orbitals in that sublevel. So that's what we're going to do when we look at quantum numbers. We're just going to come up with addresses for the orbitals. And just like I promised you, there are going to be a number of different labels we're going to need. Let's start with the first one. We've been using the number n to tell us about energy levels all along. That n has a fancy name. It's called the principal quantum number, but what I care about is what it represents. We said it represented the energy level of the orbital. Another way to look at that is it represents the size of the orbital. Because as we went up from energy level to energy level, we saw that the orbitals got bigger and bigger and bigger. The electron in that orbital could get further and further from the nucleus. Now, we started counting the energy levels at the lowest energy or first energy level where n equals 1. And we had 2 and 3 and so on and so on. There were an infinite number of energy levels. So if I'm looking at a particular orbital, I can specify which energy level I'm at and narrow it down. But that won't be sufficient to pick out a unique orbital. There are different sublevels at each energy level. So to distinguish the sublevel, I'm going to come up with the quantum number L. That's a cursive or written L, and it's called the orbital angular momentum quantum number. I don't care what it's called. I care what it tells me. What it distinguishes is the sublevel, or perhaps more meaningfully, the shape of the orbital. The s orbitals are spherical. The p orbitals are kind of dumbbell shaped, and so on and so on. Now, I'm going to come up, instead of a letter descriptor, historically, a number descriptor came first. I'm going to tell you that the rule for L is it could be 0 or 1 or 2 or anything up to n minus 1. That's pretty abstract. Let me make it more concrete for you. Remember, again, we're trying to come up with addresses for the orbitals. So let's start with the combination of n and L. When n equals 1, we're talking about the first energy level. Now, what sublevels are there at the first energy level? The rule for L says that it can be anything from 0 up to n minus 1. And when n is 1, that is 0. So the only allowed value for L at the first energy level can be 0. The number itself doesn't make a difference. What matters is how many labels I can make. I only came up with one allowed value for L, which tells me there's only one shape orbital in the first energy level. That's 1s. So n equals 1 means 1, and L equals 0 means s. We've identified the energy level and the sublevel. Now, if you got that, it's going to make more sense if I go on to the second energy level. The rule for L says that L can be anything from 0 up to n minus 1. We're in the second energy level, so n minus 1 is 1. L could be either 0 or L could be 1. And the important thing is how many labels that generates. I got 2 labels here. So that tells me there's 2 sublevels or 2 shapes at the second energy level. Those are the 2s and the 2p. So n equals 2 tells me the energy level. L equals 0 means s. L equals 1 means p. Let's go up just one more energy level to make sure we've got this. You're going to anticipate me on this one. If n equals 3, what values for L can we have? What sublevels appear at the third energy level? Okay, pause the video. Okay, L can be anything from 0 up to n minus 1. L can be 0, L can be 1, L can be 2 at the third energy level. We got 3 labels because there's 3 shapes at the third energy level. There's the 3s, the 3p, and the 3d. Now, it might be a little frustrating. Why do I need number labels for the sublevels when I already had letter labels? It comes out of the math. It's part of the complete story. But there's a perfect correspondence. We start with L equals 0. The first shape we learned was S. So I can start counting at L equals 0 and figure out the shapes. 0 is S, 1 is P, 2 is D, 3 is F, and so on and so on. Okay, 2 different quantum numbers gets us down to the sublevel. But some sublevels have more than one orbital in it. So to uniquely identify a particular orbital, we're going to need a third quantum number to identify which orbital in the sublevel we're talking about. And that number is called the magnetic quantum number. Now, I don't care so much what it's called, I care what it means. Remember that when we looked at the set of p orbitals, we had the px, the py, and the pz. The only difference between those was that they pointed in different directions in space. They had a different orientation. So ml relates to the orientation of the orbital. The math for the orbitals came up with this rule for ml. It can be anything from negative L plus 1, negative L plus 2, and so on until I get to positive L. Pretty abstract. Let's apply it like we did when we learned about L. So we started at the first energy level. Then we said that L has to be 0 at the first energy level. There's only one sublevel. That's the 1s. Now, what are the values for ml? L can be anything, ml can be anything from negative L to positive L. But for an s orbital, L is 0, so ml can only be 0. Again, the number itself doesn't mean anything. What matters is how many labels that we could make. We only made one label there for the s sublevel. What that means is s orbitals come in sets of 1. Aha! So that's the 1s, the 1s. Second energy level, we saw that we could have L equals 0 or L equal to 1. In other words, there's a 2s sublevel and there's a 2p sublevel. And it's great to be able to say these quantum numbers in words like I just did. All right, now, ML for the 2s can only be 0. ML goes from negative L to positive L. I made only one label. There's only one orbital in the set of 2s orbitals. But here's something new. For the 2p, L is 1. So ML can be anything from negative L to positive L. And that generated 3 labels. Aha! How many orbitals in a set of p's? 3 of them. So these are the quantum numbers for the 2p orbitals. 2px, 2py, and 2pz. Every orbital gets its own distinct set of 3 quantum numbers. Now, of course, the atom doesn't know which way is x and which way is y and which one is z. But the rule for ML generated me 3 labels to tell me that p orbitals come in sets of 3. Let's go one more. Third energy level. You should be able to get ahead of me. Prove that d orbitals come in sets of 5. Pause the video. Okay, so at the third energy level, L can be anything from 0 up to n minus 1. That generated 3 labels. There's 3 sublevels, 3 shapes at the third energy level. The 3s, the 3p, and the 3d. Now, how many orbitals in each sublevel? When L is 0, ML has to be 0. So the 3s orbitals come in only sets of 1. For the 3p, L is 1. So ML can be anything from negative L to positive L. I made 3 labels. The 3p orbitals come in sets of 3. And finally, when L equals 2, when we've got the 3d orbitals, ML can be anything from negative 2 to positive 2. How many labels did I make? 5 of them. How many d orbitals in a set of d? 5 of them. Okay, now let's try it from the other perspective. I generated quantum numbers and told you what the orbitals were. Let's look at the orbitals and see if I can assign quantum numbers to them. So let's say, for example, I want a unique address and a unique set of quantum numbers to define that orbital and that orbital only. So we're going to assign the first quantum number, n. And remember, that was the energy level. That orbital I circled is in the third energy level, so n equals 3. But if I just say n equals 3, that means it could be any orbital in the third energy level. I need to narrow it down even further. I want to know it comes in the set of d's, not the s's or the p's. So I'm going to need the quantum number L to tell me what sublevel that is. The rule for L starts counting at 0. So I can start counting from there. D is L equals 2. So I've narrowed it down to a sublevel, but with only those 2 quantum numbers, I've only narrowed it down as far as the set of 3Ds. I haven't narrowed it down to a single orbital yet. To narrow it down to an individual orbital, I'm going to need the ML values. And ml can be anything from negative L to positive L. So for the orbital I circled, maybe I'll say ml is -1. With the 3 quantum numbers, I've uniquely defined a particular orbital. Now, you've been very patient. Why do we care about this? We're going to put electrons in the orbitals. In the next chapter, we're going to see atoms with many electrons, and we have to fit them into the orbitals, which are spaces where electrons live. When we look at bonding in molecules, well, those bonds are made of electrons. Where the electrons live in the atom determine how they will bond with other things. They will help us determine molecular shape and molecular reactivity, and that's where we're ultimately heading. So be patient, we're almost there. Okay, we've got 3 quantum numbers here, and they uniquely define an orbital, but as I say, we're going to start putting electrons in them. I'm going to need a 4th quantum number to define the electron itself. When I put an electron in a magnetic field, this shows the strength of the magnetic field that I put them in. They will line up either with the magnetic field, so that the field lines point that way, and we call that spin up, or it will align opposite the external magnetic field, and we call that spin down. So there are 2 ways that electrons can exist in an atom. It can be spin up or spin down. We have a rule for the spin quantum number, ms. For spin up, we'll say it's +1/2. For spin down, we'll say it's -1/2. And again, the numbers don't matter. What it means is that there are 2 ways that electrons can be. Spin up, spin down. 2 labels, 2 ways electrons can be. All right, let's summarize what we've learned about the quantum numbers. We had the principal quantum number n, which is the energy level. I prefer energy level over shell, but you'll see shell in various books. We've got the quantum number, which the L, which I think should be a script L where I came from. That's the sublevel or subshell. That's the shape. Then we have ML, which was the orientation, tells me which orbital in the sublevel it is. And finally, the 4th quantum number is just for the electrons. It's the spin quantum number, ms. The rules are summarized here, but remember the only value of the rules is to generate the right number of labels to tell me how many orbitals I can have and how many electrons I can fit into them. This has all been leading to a principle by which we are going to assign electrons to a polyelectronic atom. The Pauli exclusion principle, and this is Pauli in the picture there, Wolfgang Pauli, he said no 2 electrons can have the same set of 4 quantum numbers. Here's what that means in practical terms. We saw that to define an orbital, that specified 3 quantum numbers already, n, l, and ml. So if I put more than 1 electron in the single orbital, 3 quantum numbers have to be the same. But if I have to have a different 4th quantum number, that's going to have to be ms. And I can put in an electron that has ms 1/2, or I can put in an electron that has ms -1/2. So, because there have to be 4 different quantum numbers, that says that because 3 are the same for an orbital, I can only fit 2 electrons per orbital, and they have to have opposite spins. Again, pretty theoretical, but very, very soon, I kept saying the next chapter, but really it's the next section, we're going to apply all this as we actually fit electrons into orbitals.